Introducing to functions, and this is 7-1, and so we're going to start off by looking at number 1 and 2 on your notes. You guys should know the answers to 1 and 2 already. We already learned 3 other ways to say domain and 3 other ways to say range. So I'm going to pause and you guys write as many as you can think of for domain and range on your paper. Input, okay. All right, Laura? Is for domain? For range, output. Okay, see how they go together? All right, what's another one? You can tell me if it's either for domain or range. Which one? Yes. Okay, range is Y value. Okay, what else? X value. Okay, another one, Connor? Independent variable. Remember how when we were graphing story problems, you always had to know which one was the independent variable and which one was the dependent variable, because that's how you knew which one went on the x-axis. Okay, so then the other one follows that it's dependent variable. Okay, now why do we have to have all of these words to say the same thing? It depends on what we're focusing on. So like I said, when we were graphing, we were looking a lot at independent variable and dependent variable because we had to know where the x value and y value went, what went on those axes. When we're talking about the look of a graph, we often talk about the domain and range. In secondary 2 right now, we're focusing a lot on domain. And what we're doing today, we're going to be talking a lot about input and output. That's going to be a big focus for what we're doing today. So along with today's lesson, we have a few other vocabulary words. And so number 3, pairing 2 sets of data as ordered pairs forms a relation. There's nothing necessarily special about a relation. It's just a set of ordered pairs. So it might be 1 ordered pair, it might be 20 ordered pairs, or it might be 1,000 ordered pairs. It's just a bunch of ordered pairs, okay? However, there is a special kind of relation, and it's called a function. So a function is a relation where for every input, and I'm going to underline that, for every input, there can only be one output, okay? So let me use for an example. Okay, so Graham, if I ask you what is your B5 class, what are you going to say?
Math.
Math. Don't you have an English class? Isn't it right now? Would that be possible?
Yeah.
It would be possible to have English right now too?
That's supposed to.
Well, no, but I mean, also, could you have math and English?
No.
Okay. It's not possible for him to have math and English. Okay, because that is trying to be 2 places at one time. Okay, that's not possible. All right, so Graham can only have 1 class at a time. All right, what about the rest of you? All of you have a B5 class also. All right, so Dylan, what is your B5 class?
Math.
Oh, how weird. Your class is math also. Is that possible to have more than 1 person that has math? Okay, yeah. So the input in this example is the student's B5 class. The output is math. So each input can only have 1 output. But another way that I could write this, like if I wrote, Graham has math and Dylan has math, and I could go on with the rest of you and list all of you on here, but you could all have math, okay, but that's okay. We can have all the outputs be the same thing, but it's just that, you know, Laura can have math, but she can't have math and science, all right? So that's an example of a function. An input only has 1 output. If the domain or the x value repeats, and that's one of the ways that we can tell if we have a function or not, but if it repeats, then the relation is not a function. Okay, and then the last thing that we're going to talk about as far as definitions go is a mapping diagram. Is a model of a relation that maps each input to its output. And I'll show you how to make a mapping diagram and how to read a mapping diagram, what it means, okay? So it's just a visualization. All right, so let's go on to functions and start talking about how to tell whether something's a function or not. So the next thing that you see on your paper, it says to determine if a relation is a function, and there's a couple of bullet points there. So the first one, it says if the data is given as a table or a list of ordered pairs. And that's not what I'm seeing right here on the paper, but we'll get to that in a minute. So if you have a table or a list of ordered pairs, the main thing you need to look at is if the x value is only listed once, then it's a function. If the x value is repeated or listed more than once, then it's not a function. So we'll see some examples of that in just a second, but it has to do with how many times the x value is listed in the table or in the list of ordered pairs. If you are looking at a graph, which is what we see over here to the right, if you're looking at a graph, you're going to check to see if at any point in the domain, there are more than one possible values for the range. So what I'm saying is if you look at the circle, okay, this graph is the circle. If I was to look at the point 0, that's my input. The output would be positive 3, but there's also an output of negative 3. So basically 0 gives an output of 3, and it also gives an output of negative 3. Okay, so that means that the same input is giving more than one output. The circle, if you plug in 0, so if you have an ordered pair, 0, 3, and 0, negative 3, you see how the domain is listed twice, and it gives a different output, so one input has more than one output. If I look at this other one to the right, this is kind of a parabola on its side, and if you go to, say, 2 on the x-axis, it has an output of positive 2.5 and negative 2.5. So an input of 2 has an output of 2.5, and it has an output of negative 2.5. And so that makes that not a function. The next one, down below where it says functions, this is a parabola. And this one right here is if you go to, say, 0, there's only one output for that. You put in 0, you get out 0. That's the only thing that 0 is going to give you. If you go over to 2, you get out 1. If you go to negative 2, you get out 1. Now notice that even though 1 is listed there twice, that's not a domain number. That's a range, and that's fine. So an easy way to tell this, and so we have something called a vertical line test. And so if you have a graph, a vertical line test is a really fast way to just look at it and see if it's a function. And so you can see if a function passes the vertical line test by literally drawing a vertical line, and if it touches the function more than once, or the graph more than once, it's not a function. And so that's why the vertical line test works, because if I see something like that, not a function. If I see something here, that is a function. There's no way you can draw a vertical line to touch that more than once. Same thing with that equation. And so a vertical line test is a tool to help us find the to whether it's a function or not. Okay, so the reason why these are functions is because the domain does not repeat. So at any point in the domain, there check to see if there is any more than one possible value. So they are functions because there's only one output for each input. You should write that down. Okay, the question as to why it has to do with the x value and not the y value. It is because the definition of a function is that for every input, aka x value, there is only one output, aka y value. It doesn't say anything about the other way around. Okay, so this goes back to what we said before on number 4. A function is a relation where for every input there is only one output, and that's why it has to be that way. Otherwise it's not a function. We're not saying that these aren't graphs. We're not saying that they're not equations. We're just saying that they're not functions. Okay, so that's what that is. Okay, now let's go on and see some other examples of what we're talking about. The first thing we're going to do is we're going to learn how to make a mapping diagram. And so you'll notice that right here I give you a set of ordered pairs, also known as a relation. Okay, that's a relation right there because it's a set of ordered pairs. We're going to make a mapping diagram for it. And so what you do is you are going to make 2 ovals. Okay, so everybody's got your 2 ovals on your paper. And on the left oval, that's your domain, and on the right is your range. So what you're going to do is you're going to go through your relation and look at all your domain numbers. You're going to take all of those domain numbers and you're going to list them. Now, you see how I've got 4 twice? I'm not going to list it twice. There's no reason to list it twice. Don't list it twice. And so I'm just going to write each thing one time. And then I'm going to do the same thing with my range numbers. So my range numbers, I'm going to have -7, 0, -2, 3, -8, and 13. Okay, so that's the start of my mapping diagram, but I'm not finished yet. This next part is a very important piece of the mapping diagram because this shows how the input gives us an output. And so you're going to draw an arrow from 12 to -7 because that indicates that an input of 12 gives us a result of -7. It has to be an arrow. You can't leave that arrow part off. It can't just be a segment. It has to be an arrow. So 4 gives us 0. 1 gives us -2. Okay, now here's where we have to go back because it says 4 gives us 3, so I'm going to have this. You guys, that's like one person going to more than one class at a time. You see that? You see how 4 is split in what it's doing? That right there makes this not a function. It was like Graham trying to go to math and English at the same time. Okay? All right, so continuing on. 2 goes to -8. And 5 goes to 13. Now this is a mapping diagram. So if you're told to make a mapping diagram, this is just a visualization of the relation in a different way. It's just a different way to see it. But one thing we can tell from a mapping diagram is if it's a function or not. And here again, I'm looking at this right here. That right there is telling me this is not a function. So the question, is this a function? Explain why or why not. The answer is no, it's not a function. The reason is because there is an input that has more than one output. Specifically, 4 has an output of 0, and 4 also has an output of 3. And that's the problem. So this is not a function. It's still a set of ordered points. It's still a relation. I can still graph all the points, but it's just not a function. Okay, now as far as the next question, just some ideas like how could you change the relation so it was a function. Not that we can do that. It's kind of like if you have 5 plus 2 and you're like, I don't want to do 5 plus 2. I'm going to change it to 5 plus 3. You can't do that. Okay, so we're not just changing the problem. But what would be a similar problem that would be a function? So how could I make a change up there if I was writing a new question so it would be a function? So let's have some ideas on what I could do. What are some things? Okay, Connor?
You could really take out the ordered pair one of the ordered pairs that had an output from 4.
Okay, so like maybe just throw that one out. Now, just to reemphasize, I can't just go around changing the problem, but if I was going to write a new problem that was going to be a function, that would be something I could do. All right, what's a different idea? Yeah.
Could you switch the x and y?
Okay, what if I swapped an x and y? Like I took the 4 and the 3 and I switched them around. Okay, then instead of having 4, 3, I'd have 3, 4, and then it wouldn't be any problem because I don't have any other 3s. That's another idea, okay? And then probably one other thing I could do. Anybody have one other idea that I could do? Anything else? Yes?
Change the 4.
Yeah, we could just change one of the numbers. So you could just change out to, I don't know, 16 or something. Okay. Or, yeah, I mean, you would just change one of the 4s to be something different. That's all. Okay. So those are just some ideas. If you were trying to write a function, you would just make sure that there's no repeats in the domain. Okay. All right, let's go to the next thing. So numbers 3 and 4, you're going to use a mapping diagram to determine if each relation is a function. Explain why it's a function or why it's not a function. So I want you guys to make a mapping diagram for both of those questions. And then you're going to say either yes or no. Yes, it's a function. No, it's not a function. And then explain why. Okay, so one thing to remember is that you are not going to repeat any of the numbers. As you write them down in those ovals, don't repeat them. So if you're writing them more than once, you shouldn't be. Okay, so I'm just looking at as like on the first one, I noticed on the range that I had -1 listed twice. I only wrote it there one time, okay? And so when we're doing this visualization, you just want to do that one time. Now there is some debate out there, mostly between me and Mrs. Moulton, if you should write these numbers in order from least to greatest. And my argument is no, just write them in the order that you see them. And I feel like that's more appropriate because of things that we'll do later on. And so anyway, the way Mrs. Moulton writes them is she would write like -9, -3, 6, 7, 8, and then she would write the other numbers in order. and then use the arrows to show, and that's great for a mapping diagram, but for other uses of a function, that's not how it's going to go. So I feel like just write them in the order that you see them, okay? And then don't forget that we have to have arrows showing. And one of the biggest mistakes I see that students do is they'll just do a segment like that, and that is not showing anything. You have to have the arrow there. So make sure that you've got the arrow or else it will not be correct. Now, does this make it not a function, the fact that 7 goes to -1 and 8 goes to -1? That's still a function. It's like you guys are all in the same class right now. Okay, that's something that's possible. So this one is a function, so I'm going to say yes. And really the main reason why it's yes is because each input has only one output. So they can share an output, but each input only has one output. Okay. Now if I look at the other one, drawing my arrows, 4 goes with -5, 1 goes with -3, 0 goes with 0, 1 goes with 1. Okay, that right there, even without finishing this, I can see that that's not a function because of that. And then where did I leave off? 1 goes with 1, 4 goes with 5. There's another reason why it's not a function. So I've got 2 reasons why. And then 9 goes with 3. And so this one is not a function, and there's 2 reasons why. It's because the input of 1 has 2 different outputs, and the input of 4 has 2 different outputs. Okay? So I'm going to say for this one is no. And it's because some inputs have more than one output. Okay, so that's how you can use a mapping diagram. And then, okay, so on your paper there's also a question that says how can you use a mapping diagram to tell whether a relation is a function? And so the way that you can tell by just looking at a mapping diagram is you can look for something like what we just saw. You can look for something in your mapping diagram that goes like that. If you see that in your mapping diagram, that's an indication that we do not have a function. Can anybody think of any other way we could use the mapping diagram to tell? Was there anything else as you were making your mapping diagrams that kind of clued you in? Andrew?
There's just the same number more than once.
Yeah. If there's more than one number in the left oval, so if you're writing something and you notice like, oh, I'm not going to write that one twice and it's in the domain, then that's an indicator before you even draw your arrows. So if you see that you've got, in your left oval, if you see something that you've got X and then another one, that's an indication right there because you're only going to one time and it's going to go to 2 different things. So that's how you would know that. So a mapping diagram is a quick visualization way to see if you have a function or not. Okay, so next thing is let's look at some graphs. So on your paper we have 3 graphs and you don't necessarily need to know about them, but remember that every equation has a picture and every picture has an equation. And so we have these pictures called graphs and they all have equations that go with. The question is, are they functions or not? Okay, they exist, they're there, but are they a function? So right here on number 6, this is something that we'll see next year, and it's called a sine curve. And the equation for that is y equals sine x. That's the equation for that. It's a trigonometric equation. And so the question is it a function? So how could I tell if this is a function? Jonah, what are you thinking?
You can draw a vertical line down.
Yeah, the vertical line test would be a really quick and easy way to see. Is there any way you can draw a vertical line that touches that more than once? No. At this point, people are usually curious, like, is there a horizontal line test? There is a horizontal line test, but it has nothing to do with functions. And you will not even hear about that until at least secondary 3. Okay, so just put it out of your mind. There is no horizontal line test. Okay? All right, so this one is going to be, yes, it's a function. Now, the reason is not because it passes the vertical line test. The reason is still because each input has only one output. That's always the reason why. You're not going to say it passes the vertical line test, okay? But each input has only one output. And that's the reason why. Question?
When you're explaining why it's a function or not, if you say yes, could you put one input equals sign one output?
Yeah, sure. That would, as long as you're indicating that each input has only one output, how you do that can vary slightly, okay? All right, now number 7, this is actually kind of a series of different equations. So is this one a function on number 7? What do you guys think? Why, Graham?
Because if you do the vertical line test, then it goes to.
You see, the vertical line is just kind of our tool to help us look. And also you might notice, like, some people say, well, yeah, but I could draw a vertical line and it only touches once right there. Yeah, but I can draw a vertical line that touches twice. So it's not a function, okay? So this one is not a function. And again, the reason is because we have an input that has more than one output. Like specifically, you could say that the input 0, what is the input for 0? I can't quite see that number. Like, what's this point right there?
It's
5.
5.
So 0, 5, and 0, negative 5. So basically 0 has more than one output. And so that's the reason why this is not a function, okay? So the reason is because there's an input, specifically 0, that has more than one input, or output, sorry. Okay, the last one, number 8. This is called a quartic. And what do you think? Is it a function? What are you thinking? Nate, what do you think? 4 or 8, sorry.
Yeah, I think that is a function.
Okay, I agree. Okay, this one is kind of like an exponential in that the sides, this is what throws people off right there, is those sides are like, well, are they going straight up? Like, could I draw that line and touch it? It's like an exponential in that it's still going up, but it is going to the right. It's just very gradual. So you're actually not going to be able to draw a vertical line that's going to touch more than this one time. So this one is a function. And so again, you can just duplicate what you wrote on number 6. Question?
What would we do if it was
Oh, that's a good question. So is a vertical line, so a graph of a vertical line like x equals 2, is that a function? Let's think about it. That's a really good question. So let's say that I have this vertical line like this. Okay, you guys, this point right there is, let's say this line is x equals 3. So this point right there is 3, 4. And what's this point? 3, 3. And this point is, well, maybe I'm 3, 2 or 3, 1. And 3, 0. Okay, you guys, what about the input-output thing? Is that a function? No, because 3 has every single output, and that's not a function. So good question. A vertical line is, in fact, the only line that's not a function. Every other line is a function. Okay? Good question. Okay, let's go to the next thing. Number 9 and 10, these are tables or lists of data. And so this is what we were talking about on the first page with the first bullet point. If you have a list of data, what you need to look at is you need to look at your domain. So look at your domain. Is there a repeat?
Yeah.
You guys see it? So because there's a repeat, 9, that's not a function. It's that simple. That's all you have to do. So we're going to say, no, it's not a function. An input, specifically 9, has more than one output. Okay, look at number 10. When people look at number 10, what throws them off is this. But you guys, that's like all of you being in the same class. 0 goes with -4, 1 goes with -4, 2 goes with -4. It's like all the people are in the same class. So the domain is what we look at, not the range, and that goes back to a question earlier. It's the domain that we're looking at, and are there any repeats in the domain? There are no repeats in the domain. So this one is a function. Yes, each input has only one output. You could do something like this. Each input only gives one output. You could do something like that. All right. Okay, we're going to continue on to the next thing, and how do we use functions? What's the point? Let's talk about something called function notation. All right, function notation is something like this, and so it's got an f with parentheses x, and the way we read that is we say f of x. It's not fx, it's f of x, okay? And so if I hear you saying fx, I'm going to stop and make you repeat yourself correctly this time, okay? So f of x. And then we've got another name like g of x. You can actually have any letter you want. We could have h of x, q of x, a of x. It doesn't matter. You can actually have f of t. Okay, so you can have any set of letters you want. It just means different things. And so we're going to talk about function notation. One thing that you know when you define this is f of x equals 7x minus 5 is exactly the same thing as saying y equals 7x minus 5. Now I know that for me, when I was in high school, that was terribly frustrating to me, because if these were exactly the same thing, I would rather just write y than f of x, and I thought it was stupid that we would have to write f of x. It's like, why do I have to do that? But as we start learning about functions and we start understanding, this is actually giving us a set of directions for what we're supposed to do. It's kind of like, depending on what you're looking at, you're going to use a different word. Like you're going to use independent variable or you're going to use input depending on what you're looking at. So if we're talking about functions, we use function notation because it gives us directions. It tells us what we're supposed to do, okay? So let's start with a function. So number 11, it says if f of x is equal to 6x minus 8. Okay, so first off, this function has a name, and that function's name is f. And it's equal to f of x because the input variable is x. If it was f of t, then it would be 6t minus 8. If it was f of a, then it would be 6a minus 8. If it was f of m, it would be 6m minus 8. Do you get the idea? It's the same function, it's just we're using a different input variable. And so what we do when we find f of 10, we're going to do f of 10. And so guess what it's going to be? 6 times 10 minus 8. And you're going to tell me, what is 6 times 10 minus 8? 52. So that's what f of 10 is. And that's all wonderful and everything, but what in the world does that even mean? So let's go back to what it said. It said basically y is equal to 6x minus 8, and you all know that that's a line, and you all could graph that as a line, right? So if I graphed it, y-intercept -8, slope is positive 6, it's going to be like that. What this right here means is it means that if I went over to 10 on the x-axis, I would have to go up to 52 to find my graph. If I went over to 10, I'd be going up to 52 before I found my graph. That's what that means. If the input is 10, the output is 52. So it gives us a location on our graph. It gives us a specific point, and that's what we use function notation for a lot. Okay, we find a specific location on that graph. Okay, let's try number 12. Number 12, what kind of an equation is that? I mean, it's a function notation, but what kind of a graph would we be looking at? It's exponential. One says g of x. Now this one's name is g. Instead of like the last one was f, this one is g. It's kind of like when you were born, your parents gave you a name. Why did they name you that? Because they felt like it. Okay? This one is called g because I felt like calling it that. I could have just as easily have called it h. All right? I just chose. All right? So there's nothing special about that being called g. And tomorrow we'll have something different called g of x. Okay? It's just like, you're not the only one named Laura. Okay, there's other people named that. All right. Okay, so it says to find g of 7. So that gives me my direction. What do I do? So first thing you do is you write down g of 7 equals, and then you write the function g, but instead of x, you're going to write 7. So we're going to write 2,500 times 0.6 to the 7th power, and you're going to get your little calculator, and you're going to calculate that. Now, you know that since it's exponential and it started way up here at 2,500 and it's losing 40%, it's going down and we're going to have 60% every time. After 7, it's going to be down here a ways. So where is it exactly? Okay, Dylan, what'd you get?
I got 69.98.
69.98, so approximately 70. That means that the ordered pair 7 and then about 70 is on my graph. So if I come over here to 7, this is about 70. That's what that means. Okay, so as far as what is my answer, your answer is, let me erase this right here. Depending on what the directions say, you might write g of 7 is equal to 69.98, which I know there's other decimals too. Or you might say g of 7 is equal to 70, just depending on what the directions say for rounding, but that's what the answer would be. For number 13, it says to evaluate f of x equals 4x minus 7. And so what that means is y equals 4x minus 7. And over the domain, that means that these are all x's. So one at a time, we're going to let each of those be an x. So first, f of negative 10. And that means 4 times negative 10 minus 7. and then f of negative 3, which means 4 times negative 3 minus 7. F of 2, 4 times 2 minus 7, and f of 5, which is 4 times 5 minus 7. So evaluating each of those, I get those numbers. So the question is, what is the range? And so the answer to that is each of the range values in order. That's the answer. So trying the next one, g of x equals 4 to the x plus 1, and my range are those four numbers. So write it out. Okay, 4 to the negative 1 is 1/4 plus 1, and that's 1.25. You can use decimals for this. 4 to the 0, remember that that's 1, plus 1 is 2. 4 to the third is 64, plus 1 is 65. And 4 to the 7th, plus 1, 16,384 plus 1 equals 16,385. So I'm going to take these numbers right here. That's my range. So my answer is that. So what each of those is saying it's saying that if I put in negative 1, I get out 1.25. If I put in 0, I get out 2. And so, for example, that means also that if I was to graph this equation 4 to the x plus 1, that the point negative 1, 1.25, or 0, 2, those are points on the graph. And so that's what that means. But this is my answer to that question. But let's do a couple of functions here. So let's do number 15 and number 17. I want you guys to try both of those, just modeled on what we just barely did. Okay, so h of m, the reason it's called h of m is because I decided to call this function h, but it's of m because that's the variable that I'm using in there. So if I used a different variable, it would be called something different. Okay. Now also let's just be clear that this function h of m is the same thing as the equation y equals negative 12/5 m, or x, minus 1/5. So if I was going to graph that, that is linear. It has a y-intercept of negative 1/5. It has a slope of negative 12/5, so it's going to be going like this. Okay, that's what we're looking at here. And so just to understand that we're talking about a line, okay? And I'm wondering if I went to 7 on the x-axis, where would I have to go down to get where the line is? So your answer should go along with that idea. And so you don't have to do all of that, but I'm just trying to explain to you like what this is talking about. And so to do h of 7, all you need to do is just plug it in. Okay, I know you guys know negative 12 times 7 without a calculator because you had to learn that before school started. So negative 84 minus 1 divided by 5, so that's negative 85 divided by 5, and you guys can do that. Try to do stuff like that without a calculator. You don't really need a calculator for that question. It's negative 17. And so that's what h of 7 is. It's negative 17. So that means, and you don't have to write this, but it means that if you went over to 7, you'd go down to negative 17 to find the graph. That's what it means, okay? All right, now let's take a different look at this, and let's go to number 17. Okay, again, we're talking about a linear equation, okay? We've got f of x is equal to, and we can see that that's slope-intercept form. If f of x equals 30, you guys, what's another name for f of x? Y. So what I'm saying is I'm saying if y is equal to 30, you tell me what x is. So this time I'm giving you the output. Give me the input. So how could I do this? Who can tell me how you approach this problem? Okay, Joanna, what'd you do?
I did 2 over 5x equals 30, and then I multiplied 2 over 5.
What happened to your 12? And what do you get when you do that?
I forgot to do the 12, so I.
Okay, so I'm going to have, 21 times 5, and so that's 105. Okay, so that means that if I was looking at this graph, and I don't really have space to draw this, I'll just draw it over here. If I was looking at the graph, y equals 2/5 x minus 12, it's going to look something like that. And so if I say, I know that x is or y is 30, that means go up to y to 30. How far would I have to go over to meet that graph? Where would the x be on that? So the answer would be at 105. If I go over to 105, I would go up 30 to be on that graph. And so this is just a perspective change. We're just looking at this same problem, or the same type of problem from a different perspective is all, okay? So in this answer, you're not going to write f of x or anything like that. You're just going to write x is equal to 105 because that's the answer to that. Find x is 105. Yes?
Wouldn't it be like y is equal to 1.5?
No, because y was equal to 30. We were told that. That was given to us in the problem. So we were told what y is. We had to find x. Okay, let's try something that's a little bit different. Let's go to number 18. 18 is going to be pretty different because number 1, it's exponential. Number 2, you're limited in how you can do this. And I'm very limited in what types of questions I can ask you because of the types of tools you have. So if we say g of x equals 81 and g of x is equal to 3 to the x power, what am I going to write to start this problem? What will I do?
81 is equal to 3 to the x power.
At this point, you guys do not know how to solve for an exponent that's a variable. That's not something you're going to learn for a couple of years. And so right now, the only thing you can do is say, well, 3 to what power is 81? And you can start guessing numbers. Is it 3 to the first power? Is it 3 to the second power? What is it? It's 3 to the fourth power. So x is equal to 4. So on questions like that, it's going to be something that is going to be relatively small because you're going to have to guess and check and see what the right answer is. Okay? And so that's the answer to that question. Let's take a look at number 20 just because that's similar in nature, but it looks really intimidating. And so if we look at number 20, it says f of x is equal to 2/5 to the x power, and f of x is equal to 64 over 15,625. So first, the setup. How would you set that up? Okay, how would you set it up? Who can tell me how to set this up? What am I going to write? Yes.
64 over 15,625 is equal to 2/5 parentheses exponent x.
Yeah. So let's think about what this means because it looks pretty intimidating because number 1, all the fractions, then we got the parentheses and the exponents and everything. So remember that 2/5, like if we said 2/5 to the second power, that would be 2/5 times 2/5. And that would equal 4 over 25. And so really, I just need to find out 2 to what power is equal to 64 because it's going to have to be the same thing for the 5. So 2 to what power is 64? Can you figure that out? What is it? 2 to the 6th power. So if I say 2 to the 6th power, then what is 5 to the 6th power? Is that 15,625? Then that means that 2/5 to the 6th power is equal to 64 over 15,625, which means x is equal to 6, and that's the answer to the question. So you'll be asked some questions like that, and so that's how you would answer those questions. Okay? All right, next thing. We're going to do a couple of problems like this. They're similar to what we just did, where you have to kind of figure out which way to set them up. So which perspective are we looking at? And so let's have you guys, I'm going to pause and have you guys work on these 3 questions or 4 questions, and then we'll come back and address a few of them, okay? Okay, for number 21, just setting that up real quickly, since f of x is equal to 1/5 to the x power and f of x is equal to 1 over 625, I would know that these two have to be equal to each other. So that's one hint that I can use to set this up. So 1/5 to the x power is equal to 1 over 625. I know that 1 to any power is 1. So the key is 5 to what power is 625. So you can just try some numbers and find the one that works. So Seth, what is it? 4. So x is equal to 4, and that's the answer. Now, by the way, you guys, that means that at the point 4, 620 or 1 over 625. That's where these two graphs, that's where they're going to meet up. This is a system of equations. So if I was to graph this equation, 1/5 to the x power, that is an exponential decay. If this is 1 and it's going down like this, that's what that one looks like. And then if I graphed y equals 1 over 625, that's a horizontal line because it's just y is equal to a constant. And so it's going to be like this. And so the question is, where do they meet? And this point right there is 1 over 625. Obviously, my graph is not to scale, but that's what we're doing here. We're solving a system of equations when you set something like that up. And so that's just a little aside. By the way, that's what we're doing, okay? And it's just good to know things like that. Okay, number 22. This is a linear equation. I know this does not look like y equals mx plus b, but it actually is. You could separate that to be negative 12/7 x plus 1/7. That's exactly the same thing. And then you could graph that if you wanted to. Okay, I'm not out to graph this. That's not my goal here. But what I'm trying to do is I'm trying to find what x is equal to. So since both of these are equal to g of x, I'm going to set them equal to each other. Who can tell me how I solve that equation? What do I do? How do I solve an equation like that, Connor?
First, you would times the 12x, negative 12x plus 1 divided by 7, times that by 7, to get rid of the division, and then times the negative 8 by 7.
Yeah, we're going to multiply both sides by 7 to get rid of that fraction. So I'm going to end up with negative 12x plus 1 equals negative 56. And then you're going to solve that from there. So negative 12x is equal to negative 57. And you guys just leave it as a fraction. That's fine. Okay. So if I plug that in for x, I'm going to get negative 8 in both of them. Obviously, I'll get negative 8 right there because that's the only thing I could get. But okay, the next one, number 23. 7 to the x power is equal to 343. So you're just left to find, like, okay, 7 to what? Try the first power, second power, third power. What is it? Third power. And negative 3/4 x minus 18 equals negative 36. That's how you're going to solve that one. And I'm just going to leave that one. You guys can figure that out. It's not a hard equation to solve. Okay, let's go to the last section of this lesson. This is, again, looking at the same types of problems, but with a different perspective. And so on the left, I have the graph f of x. It's a line. Why did I call it f of x? Again, because I chose to. I could have called it anything, all right? But I called this f of x. And so looking at that graph, the first question I'm going to ask you is, what is f of 2? So we need to stop and think about, what am I saying here when I say what is f of 2? I'm saying f of x versus f of 2. That means that x is equal to 2. Because 2 is in the place where x is supposed to be. And so what that means is, it means my ordered pair is going to be 2 something. Because 2 is the x value. So that means if on my graph, when I go over to 2 on the x-axis, where do I go to get to the line? How far up do I have to go? So I go over 1, 2, and I'm going to go up 1, 2, 3, 4. So 2, 4 is the point on my line. So f of 2 is 4. And that's how you figure that out. So you think about, well, I was just given what the x is, so now I find the y. So do number 26 then. What is f of negative 2? So if x is negative 2, I find it's really helpful to do that little ordered pair thing, and then it helps me kind of focus on what I'm looking for. So I know that I'm going to go to negative 2 on the x-axis, and then where do you go to find the graph? Where do you go? Anyone? You go to negative 2 on the x-axis. How do I get to my graph then? Go to negative 2. So negative 2, negative 2. That means that f of negative 2 is negative 2. Okay, number 27. F of x equals 1. So notice how this question is different. This one is telling me y equals 1. So write an ordered pair. Where's 1 going to go in your ordered pair? Okay, so you're gonna have something 1. So you guys looking at your graph, go to 1 on the y-axis. Where are you in relation to x? 0, right there. So go to 1, and there you are right there. So 0, so x is 0 if f of x or y is equal to 1. So do the last one, 28. If f of x is equal to -5. So again, my suggestion is do that ordered pair thing. That's probably really helpful. Okay, but go to -5 for y, and then where would you go for x to get on the line? Okay, so who can tell me that? Let's give me a hand. Helen? -4. Do you guys agree with -4?
Yes.
Okay, -4. So that means that -4, -5 is a point on this line. So yeah, sure enough, that's correct.